x0, this is x1, this is x2, through to, well, maybe this is x capital N. And all I'm doing is finding those solutions. The un minus 1. I just find n values. That's all. Somehow. We still need to talk about how. But somehow I find them. And then I start to think, hey, the solution here, or maybe the solution here in this Pacific Ocean, through the equations that I have, of course, depends on the solutions there and there, right? For example, the velocity here will depend on the pressure I have there and the pressure I have there, but it also depends on the velocity I have there, right? Because as I said earlier, all of these things are coupled together. So when I start translating these complex equations to relationships between the u's at each of these points, I will probably get a large set of coupled equations out of it, right? But it's now just a system of equations for the u's in each of these grid points. And even if there are a million grid points and every grid point has 5 unknowns, I don't care. It's only 5 million unknowns with 5 million equations. My computers are big enough that I can solve this, no problem, right, on the computer. So the first step is that we do this, that we say, okay, instead of wanting the solution everywhere, we just want it on the grid. And then my question to you is, what if I now want to have the solution right here? Because this Pacific here may be Hawaii. You know, I'm interested in the wind on the big island. And it's not in the grid point. What would I do? I can take a finer grid, but I don't have enough computer power for that, maybe. I could shift the grid, I heard that, so that the grid point overlaps with that exactly. But that may be hard, because then the next thing I know, somebody in Tahiti wants to know it, and has just shifted my grid, and Tahiti is no longer on it. Okay, so I keep shifting, don't want to do that either. But I could just interpolate, right? So if I have a solution here, 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 and here, I can probably find a pretty decent approximation to something in the middle. You can take some sort of average of them, interpolate it. In other words, if I have the solution at a bunch of points, I can probably find a solution that is okay, and that's all we're looking for, in between those points. If I want a more accurate solution, I got to compute it for more points, right? This is a simple thing. There's no such thing as a free lunch, right? If you want accuracy, you got to do it for more points. Now, this opens up a fantastic area. Several. One is, there are gridders that look at the domain and create a nice grid for that domain. And there's all sorts of ways you can do this. I'm a very simple gridder. I look at the domain and I want to put in straight lines like this, because I like working with these types of grids. Because computationally, they lead to simpler things. But there are people that like using triangularization. So instead of having these straight lines, they grid something like this. Anybody from near Puget Sound? So you recognize this? So this is a simulation we did on Puget Sound for tidal flow modeling. And everywhere there is a vortex of a triangle, a point in the triangle is one of these grid points. They're not as organized as nicely, but these points is where we compute a solution. And guess what? The closer we get to the land, to boundaries where things are changing faster, the more points we want, okay? Out here, not much is happening really. Sort of steady flow, we sort of know what it is. It doesn't change very rapidly, it just changes only with the tides. I don't have all sorts of small disturbances or turbulence or small eddies of a river coming in. All of these things happening at small scale, don't have any of that. So I can take what we call a coarse grid here. There's only a couple of points in which I need to know the solution, and then I know it pretty much everywhere. But here, where there's a lot of stuff happening with a river coming in and all sorts of, you know, jets and eddies here, I need to have a lot of points. So much, in fact, that you can't see them anymore. Right? A lot of points there together. So this actually took one of my students about 2 months to create this grid, to get it just right. It seems very simple to do this triangularization, but there are all sorts of things you have to be aware of. For example, if I do a grid here and the triangle is completely skewed, almost squashed together like this, then my equations don't behave so well. It's just too skewed. And when I actually look at the equations and then how these equations solve themselves on the computer, I get problems. Now, I may have too big of an error. Now, so there's a whole science behind this, that when you start translating these equations on these grid points, how they behave. Okay, so but they look very fancy, I think. We like looking at these things. We've done one for Elkhorn Slough here in Monterey Bay. Right? This is the grid. And I gave you the answer, but I always ask, what's this thing? When I show that to people, that's actually the train track. It's a little bit higher, so there's no flow going there. There's just flow here in this little area here under the train. Okay, so that's Elkhorn Slough. Again, takes a long time to think of these types of grids. Here's a grid on the airplane. Now, obviously, this is not just the airplane itself that we're gridding, but also the flow around it. But I won't show you that because it's so hard to see these things grow in 3 dimensions. But in 3 dimensions, just little tetrahedra. So not triangles on the surface, but tetrahedra volumes in 3 dimensions. And you can see some things here near this edge here, the leading edge of the airplane wing, very, very dense grids because a lot of stuff is happening there. So huge differences in pressure and so on. You can actually see the pressure distribution on the wing here. Blue is very low pressure. Why would the top of an airplane wing have very low pressure? Well, they're better. If it wasn't, we would be in real trouble. Yeah, because it's the pressure difference between the top of the wing and the bottom of the wing that keeps this plane up. And so we like seeing very, very low pressure here. And these low pressure areas, the true low pressure areas where most of this lift is actually near the front of the airplane wing. Okay? So if the back of the airplane wing damages a little bit, don't worry too much when you're looking out and you see that fall off or break. But if the front falls off, you better get out, okay? Now you can do other things, like this is just a little simulation, very simple thing. But as you're moving something, this is gas going through a reservoir. You see, as the gas is moving, you see what the grid is doing? Can you see that? Very hard to see, but as this gas is moving through, if you looked at this really carefully, you can see the grid change. So locally, we're putting in more grid points because it's much harder to calculate some of this, this gas flow in those regions where the gas and the oil come together. So we do what we call adaptive gridding. So there are all sorts of wonderful tricks that you can play to get good solutions. The question I still haven't answered, and I'm going to take 3 minutes for this, and that's the end of your math class, is how do I do the translation from these equations onto the grid? Okay? And there are whole courses at Stanford called numerical analysis courses, finite difference courses, finite volume courses that give you ways to do it. And there's all sorts of different methods, but they're basically all the same thing. So that's what we're going to talk about, and it's something like this. But I'd like to use the board, so if we can just raise this, and I'll close this. And I'll just give you a quick idea of how this is done. And then you can probably use your creativity to understand that this is a little bit more complicated in multiple dimensions, but it doesn't matter. It's all the same thing, really. All right, let me just use this. B, I think. Yeah.